Thank you everyone for coming. My name is Nathan and I'm here along with Adam and Gabriel. We're going to talk about our senior design project, the Robotic Hand. So in recent years, there's been increasing interest in robotics and optimization of robotic hands, and this is due to the wide range of potential applications it has. These applications range from prosthetics and surgery to even assisting with tasks that are too small or too large for humans to be able to handle. The Robonaut 2 was created by NASA as an initiative to be able to explore space. This robot has a highly intricate hand that's capable of dexterous manipulation. It has 12 degrees of freedom in the hand and 2 in the wrist. But unfortunately, hands like these are not a viable option for consumers because they are very expensive and they costing up to $100,000. On the other end of the spectrum, we have the Open Hand project, which is a $1,000 hobby-level project. It is open source, and the purpose of it is to be able to help amputees get easy access to prosthetics. It's 3D printed, and it uses electric motors for muscles and steel cables for tendons. And then, although it's a lot less expensive than robots like the Robonaut, it uses mechanics that adversely affect the joint coupling. Our project motivation in creating a robotic hand is to protect people from working in dangerous environments and handling hazardous materials. We want to be able to extract things from the deep sea, handle radioactive parts at nuclear facilities, and retrieve things from floating buildings. And our project goal is to bridge the gap between cost and dexterity and develop an anthropomorphic manipulator that offers a higher level of dexterity than those that are currently commercially available. And by high dexterity, I mean 10 degrees of freedom in the hand, 2 for each finger, and a remote parallel human interface that a user can wear a glove with flex sensors, and this can be mapped to the movements of the robotic hand. And because it's anthropomorphic, which is means that it's modeled after an actual human hand, it's familiar and intuitive. We also want it to be low cost with research, development, and prototyping, all of that totaling less than $1,050. And we want it to be robust, so faring at least as well as a human hand would in the same environment. Some of our project specifications, I already mentioned high dexterity. And we also want it to have puppet fidelity, meaning that the difference between points of interest of the human hand and the robotic hand to be within 10 millimeters. We want it to have a very short response time, so less than 1 second. And we want it to be waterproof. We want it to be completely submerged in water for under 5 minutes without fail, and as well as heat resistant to withstand temperatures of 120 degrees Fahrenheit.
So then, to expand on all those, these are some of our major distinguishing design features. That was just a summary. We're about to get into all of these right now. But first up, we have tendon servo actuation, which is the method by which we're going to be moving our fingers. The material choice for our fingers is, in our current iteration, is high-density Delrin plastic. Then Nathan was talking about the 2 different aspects. We have the actual robotic hand, and we also have the physical implant. For the rest of the presentation, I'm going to be saying like pocket hand, which is the robotic hand. And then finally, we are going to spec out our electronics in the rest of the presentation as well. Next slide. All right, so tendon servo actuation, surprisingly similar to muscle tendon actuation. And so this is an interesting model because it mimics human anatomy very well. And so in a regular arm, your tendon attaches to your bone, and the muscle pulls on the tendon, which pulls on your bone, moving your arms every which way. In the tendon servo actuation, the muscle is replaced with a servo, and the tendon is replaced, in our case, a nylon string or something like that, which is tied to the end of the finger, strung through the rest of it, and when the servo moves, then the finger moves and pulls the string along. And the advantages, like we were mentioning, it's a nice model to mimic human anatomy. So there's a lot of space saved up in the hands, a lot of stuff back here where the servos are going to be placed. It's easy, simple to manufacture, low cost, and easy to control. Since we have our digital outputs of the servo, we can map the position of the finger to the different servo positions. Disadvantages, it does have a limited lifting capacity. It's actually relatively weak. We could turn this up, we could push the finger back down just using minimal force ourselves. And also space. You notice I put space in advantages and disadvantages. One of the disadvantages about the servos is that they do take up a lot of space. And all the strings, the servo horns, they require a bit of finagling to get all right into the right place, which has been one of our major roadblocks thus far. At the bottom, I mentioned some other alternatives that we considered early on, such as pneumatic actuation or hydraulic actuation. And pneumatics could typically be light and compact, but they are harder to control. And hydraulic actuation, we do find high power and high strength, which you see in like construction vehicles and stuff like that. But there's a lot of variables that we can't account for. It's a bit too complex, it's beyond our scope. Next slide. The next major thing we wanted to talk about was the material that we chose for the fingers. One of the major things we were talking about was robustness of the fingers. So originally we did like 3D printing, then we did wood, and we finally settled on Delrin plastic. I have some statistics up here. Temperature range, negative 20 degrees Fahrenheit all the way up to 120 degrees Fahrenheit. After some rough research, we found out that's about just about the maximum end of how hot humans could touch. So it's at least as good as that. The yield strength is about 9,000 to 11,000 PSI, and it's cheap. It goes about $5 to $5.50 per foot. Pretty neat. The other major reason why we went with Delrin is that it's convenient. In terms of manufacturing, we're able to do all our manufacturing in-house. This density, high plastic, meaning we could machine it using typical like wood and metal methods. And I put up a picture, you can kind of see the raw edge. And then again, alternatives, we talked about 3D printing, we talked about metal, which is good for like antibacterial sort of stuff, but it's heavy, it's expensive. Wood, also weak, really light though, but also really breakable. We also considered 3D printing at a point, but that was just a lot more convenient for us, a lot quicker to turn around prototypes using our in-house manufacturing as opposed to going through the 3D printing infrastructure here. Next slide. All right, and so, like I was mentioning earlier, we have two major parts. The puppet teleoperation is going to be one of the major aspects of our design. And so, the major advantage of this is that we have two types. We have organic input going in, and we have organic output going out. So that means that you could be controlling this thing from a distance, like Nathan was saying, with intuitive, easy to learn controls. So super cool, but it's also really complex when you start graphing some of the more complex human motions. Like we only have 1 degree of motion on our current finger, but the actual degrees of freedoms are quite innumerable. Alternatives, traditional remote controllers, joysticks, buttons, keyboards, stuff like that. Like I mentioned earlier, that's more like an inorganic input going out to an organic input, so there's some kind of disconnect over there that we didn't want to deal with. And then some other alternatives we discussed were preset configurations. Some hands that we researched, they came with a single grasping motion, right? So they averaged up a bunch of data, and they were able to get like a single grasping motion. And that one hand is good at that one grasping motion, but we wanted more flexibility. We wanted to be able to control each individual finger as we needed. Next slide.
Now we will tell about the selection of our microcontroller. We choose Arduinos because Arduinos is cheaper, and the Arduinos I have two. The two was simple Arduinos, and they have all these specifications. And for our project, the most important thing is because we need to measure a lot of things, and they want to tell a lot of fingers point to where they need to go. And we see for that we need to choose the Arduino method because there isn't enough points analog input pins in the cheapest Arduino. And another good point about that is because it's much more faster and there is much more memory. For this reason, we are choosing Arduino Mega for our project. But now that we only have 1 degree of freedom, we are using Arduino. But in the next iteration of the project, we are putting this Arduino. Now I will tell some things about the servo selection. I looked for some servos with the same torque. This torque can move the hand. And there is a lot of specifications. The speed are also similar, and for this one is better. And the only problem for this one is the precision, but there isn't a lot of problem with the overshoot of that. And we are choosing this servo principally because the price is 3 times more cheaper. And in one hand we use like 5 servos. Multiply 5 by 20, $100 more. And this is the reason for this servo. This is a basic schematics of how we move one finger with these electronics. Here we have the flex sensor, and I measure the voltage here, and the Arduino computes this voltage and make one mapping and tells the servo moves to some place. And here is a basic flow chart showing all the process of how we control. First, we have sensors in the glove. When we move, changes the voltage, and we measure. And this goes into wires in the microcontroller. Microcontroller does some calculations. And here we have a silo that in the future will be wireless. But now we are using wires, and the silo comes in the servos and control the servos. Tells to the servos to go to a certain position. And the servos communicate, drives power with the tendon treats and move the fingers. This is the basic idea about the controls.
And so in this next part of the presentation, we wanted to talk about the current work that we have up until this point. Right now we have 3 different iterations. You can see on the far right, or left for you guys. That was the project when we picked it up originally from the group last year. They went with a 3D printing build. You can kind of see the pink foam in the background. That was a really nice design. It was a bit rickety. It was kind of brittle. It fell apart really easily. They used fishing wire. It worked really well. But for our next project, we wanted something a lot more robust. And so we went with this model over here. There's the cat on top, and you can kind of see the hand and the puppet right next to each other over there, and the brown Daiso glove that we were using. But wooden fingers, a lot more robust. We used little butt hinges, and we used springs to pull it back into motion, which the other hand didn't have originally. It had 2 strings for both flexion and extension, which is pretty interesting. In our current iteration, you can see our finger build right here. It's similar to the last one, but we kind of chopped up the shapes a little more and moved the hinges down from the top into the middle to mimic human anatomy a bit closer. And those are round standoffs, and those work really well. And you can see the springs that we have over there. You can see the servo down there. Oh, that was a good day. All right, next slide. This is the cost analysis. I just wanted to show you guys some of the stuff that we were buying up until now. So this is our current bill of materials, estimated for a total of 5 fingers with 1 degree of freedom. The total cost is running us about $160, so pretty good. Future goals, we do want 5 fingers. Right now we've been messing with a single finger. Just going through the kind of proof of concept, making sure we have it right now. And so hopefully, we just got our materials today actually to build the rest of the fingers, but we're also interested in the 2nd degree of freedom, waterproofing, wireless operation, and we were starting to look into testing just this past week, grasping strength, master servant, master puppet fidelity, and so, and then farther in the future, kind of overcasting, it's only a hand right now, but ideally this would be like a full, arm one day, hopefully a full operating humanoid, but that's still much further in the future. Right now we're interested in the hand, but some of our references, and we'll take questions now.